Well, the question is, what about the performance and implementation issues? One thing, as we've said, is there's less storage per core, and we're always challenged when we reduce the amount of memory, because if what we need isn't found where we sit at a very close distance, we have to go get it somewhere else. Right? This is not an old problem. Disk, for example, out-of-core algorithms, disk was far away. In a sense, it's indistinguishable. It's all a matter of time and space scales, the granularity of the transaction. In addition, of course, data motion is expensive. The amount of area devoted to a chip to perform computations, the density of that computation is growing, but the amount of interconnect off the chip isn't really changing very much. That may change soon, but again, there's a limit to how far that can go given current knowledge. Of course, on the other side of the story, computation is very cheap. So if we're thinking about how to cope with technological change, one thing we can do is look at algorithms that make a favorable trade-off of computation for data motion. I've done work in this area in defining new algorithms, worked with Philip Kaloa and Peter McCorkadale at Lawrence Berkeley Lab in taking a solver for a free space Poisson problem and reducing the quality of information to mitigate the global length scales to reduce the amount of computation. Of course, the Holst-Bank method is another method. Mike Holst sitting here in one half of the team from UCSD, which also uses the same general idea of using a reduced description of the data to reduce the amount of global information exchange. Very important in utilizing these technologies. Okay? Now, why am I in business, and why are those of us who do these sorts of things in business? The reason is that there's an awful lot of hand coding. There is no magic compiler that will make it all go away. Now, you wonder why this picture might be. This is a story of the frog prince. And of course, the princess kissed the frog, and the frog turned into a prince. The trouble is, in this business, there is no prince. There's just a frog. And that's the way it's going to be, probably for a long time. There is no magic here. You have to do it, and you have to learn it, and you have to know how to do it. And it's a very specialized knowledge. That means that if these technologies that I described earlier begin to change, you can bet that the recipe for writing efficient or high-quality code will change as well. Of course, what we like to do is try to insulate users from that change, but at some point, the advantage of looking at things in a certain way begins to diminish as the new techniques that favor these new technologies show more of a promise. Parallelism is not a substitute for a good algorithm. Again, good algorithms, in addition to being able to mitigate the global load imbalance, the global communication cost, are also important from another aspect, which is that they can reduce the complexity of the algorithm. And parallelism can't make an n-cubed algorithm an n-squared algorithm. Not unless your number of processors grows with that, and that's pretty hard to do. There are two watchwords of my field. I call them the two mantras of high performance. One is that domain-specific knowledge is important. It's good to know the problem you're solving, even the initial data, the boundary conditions, even the way the data will be interpreted and used later on. There's a big advantage to be made by using that and incorporating that knowledge. And there's an awful lot of folklore in how to use information about locality, in particular, to try to improve performance. The other one is that for every time you increase your performance milestone, whether by number of processors or simply raw speed at which you compute the solution, there'll be a significant time investment in programming to achieve that. These things do not come for free. So it is not true that you can go from 100 processors to 10,000 processors so easily. It's a lot of work. Staging it, going maybe from 100 to 1,000, in some cases maybe what's needed. Other cases, maybe there's a certain thresholds that are crossed, that maybe that you go to 100 processors, there's an enormous amount of work. Maybe it didn't seem there was such a big investment at 1,000, but often there is, and it's problem dependent. And again, that domain-specific knowledge and realizing that. So it can get more complex, right? There are a number of different performance goals. When I teach parallel processing, I tell my students what the various things we want to do are. One is that we want to minimize serial sections. I put these in gray because I won't be talking about them today in much detail. That is the amount of computation that won't run in parallel. That can actually be part of a conscious policy decision. With a large body of code, there may be little payoff and much expense to parallelizing it. It may be a decision to limit performance in a certain way because it keeps development costs within reason. The other one is to maintain balanced workloads. Some applications, the irregular problems, will distribute the work unevenly in space and time And that means that some effort must be made to keep the workload shared more or less evenly. The other one, probably the most important, is to conserve locality. We talked about that earlier. The idea is that you don't have, if you have limited memory, you have to keep everything you can there and avoid having to go off chip, off board, off into another network, into another universe to find that data. The last one is the one I will focus on today for the remainder of the talk, is how to hide communication delays or render them benign. Now, in the case of the method I worked on, the bank host algorithm, rendering them benign is the approach that's taken. That is, you make them small enough they're not there anymore because you make them go away. The other one is to actually hide them by overlapping them. And let's see how that works. Okay? First, it's important to look at some of the software technologies that are used. The tallest mast on the ship of high-performance computing is MPI. And there's no question today that most application software is written in that runs on high-performance computers. In fact, you could simply call them MPI computers, and that would be synonymous. This model is ubiquitous then, but it is low-level, and also, importantly, the ideas behind MPI are really about 20 years old. That is, maybe a little bit more, actually. The early message-passing parallel computers came out in the early to mid-'80s, so it's been almost 25 years. Or about, and technology is different now, as we've seen. The other problem is that pointer-based structures, which are used a lot in irregular algorithms, are not really supported at MPI. You have to do all the hand coding yourself. This is part of what makes the adoption of new architectures and new technology difficult. OpenMP and threads. How many have used OpenMP or threads? A few. All right. MPI? A little bit more, okay. OpenMP lacks a locality model. That is to say, MPI always tells you you either have it here or you have to send a message or receive a message to get that data elsewhere. And you can also have communicators and create hierarchical communication domains. The problem is with MPI and threads is that without a locality model, there's really no way to deal with some of those exotic interconnects that I showed you earlier that might exist in the future for multi-core processors. It is true that SGI has extended OpenMP with new types of pragmas, that is, little annotations that look like comments in a program to deal with that. It's not a standard. Hopefully it will be one day, but it's a glaring omission from that model. The other approaches, of course, are a little more exotic. Cell and CUDA, which is the environment that NVIDIA uses for its products, are very specific to the hardware. There's no possibility of portability. You can't take a cell program and put it on an MPI computer. It simply won't run. And so, again, there's a problem because you invested in that technology. If it goes away or it's changing, then you've got some problems in realizing the continued performance and use of that software. OpenCL is another technology which is available now. It looks a lot like CUDA, so I'm not sure in truth how much it really does for improving portability, because we'll have to wait to see, but it may impose a particular view of the hardware that may or may not stand the test of time. I don't know yet. That's a hard one. There's thread building blocks, Fortran 90, and so forth, a number of different techniques. And then lastly, there are frameworks targeted to specific problem classes. And here, we try to avoid dealing with the parallel as much as we can by incorporating the expert's knowledge. And I hope that's I think that's the approach that is emerging here at Simula. Because in addition to having to parallelize code to make it run efficient, it's important to recognize that many are users who probably want to focus more on the domain science and less on how to the mechanics of running the program. The analogy is with databases, relational databases. A database is a system where you say what it is you want, but you don't say how it is you're going to get it. So give me all the books that have a title, in the title the word FEniCS in it, and they'll find them. On the other hand, you don't actually prescribe how that's to be performed. And whether that relational model really works in this field, except in specialized domain areas, is open. Okay, let's dig into hiding latency now. A thread is a unit of execution in a program. It's a stream of instructions that run that usually share an address space with other threads that run together. And multi-threading is, of course, how we realize high performance on multi-core processors. That's one way.